I'm happy to hear from anyone who can guess today's background before I say it. It's the small town of Cathcart, which is in southeast New South Wales. If you go all the way down the coast to Eden and then decide to drive along the Victorian border up into the Snowy Mountains, you go out of Eden, you come on this really windy mountain road that's super nice to drive up onto the Great Dividing Range. And the Great Dividing Range is quite steep near the coast there. You get up to about 1,000, 1,200 meters. And the first town you run through is Cathcart, which is behind me. It goes back to the 1850s and 1860s when it was called Taylor's Flat, not to be confused with Taylor's Arm, which is up on the north coast near Scott's Head sort of area. And it's sort of a little outpost town between Eden on the coast and some of the sheep country towns of sort of snowy mountains like Bombala and places like that. Really nice place to pop through. There's a lot of nice old buildings that go back a long way, and these are just some of them. And because it's quite close to the coast and quite high up, you get some nice foggy, cloudy days around about winter that make for some really good photography. Okay, so in the second half, what I want to do is start to play around with this commutator that we got in the first half of the lecture. So if you remember back, we started with this idea that we could have two operators that were simultaneously observable. And what we found as a mathematical requirement for that to be possible is that those two operators must commute. In other words, they must have the same result whether they're in one order or the other order. What that basically means is that the product in one direction minus the product of them in the opposite order is equal to 0. And we built a little mathematical concept for this that we call Commutator Bracket, or Commutator for short, where we basically just put those two operators with a comma between them in the square brackets. And if we've got one written like that, A comma B, what we mean is just take AB minus BA. And if that is equal to 0, then the observables connected to those two operators can be measured simultaneously. Okay, commutators turn out to be very, very important in quantum mechanics. They'll come up again later on if you start to look at time evolution, and again they just pop out of the maths. And the reason why I want them is that they also turn out to be very central to uncertainty relations, which is where we're heading in this course this week. So in this half of the lecture, I want to do two things really quickly. The first is I want to show one key relation for commutators, which is that if you basically reverse the order of the two terms in the bracket, you end up changing the sign of the commutator. It's all of 4 lines of algebra, so we'll whip through that one fairly quickly. And then the second thing that I want to do is give you an example of two real operators in one of these commutators, so that you can have a look at how they actually really work from a quantum mechanical perspective. So let's get some paper. We'll do this first one because it's really, really quick. And it's very useful to know how to do this on the fly because a lot of commutator relations turn up a lot when you're doing the mathematics of sort of uncertainty principle and other aspects of commutation in quantum computing and quantum mechanics. So what we have here is our commutator A comma B, and it is equal to AB minus BA, okay, as we put in the last slide. And I wanted to write it this way because it actually is one of the two ways that I remember relations with commutators. Let me just get this minus proper. First is I remember commutator as in what it looks like as, hopefully some of you are familiar, probably from your parents, of a Swedish band from the 1970s called ABBA. And when it came to commutators, I always used to use ABBA as my mnemonic from Mandarin commutators. So one of the two ABBA versions that I have is exactly this. If I've got A comma B, all I'm doing over here on the right-hand side is writing ABBA A, B, B, A with a minus sign in the middle because I don't like them. It's a negative thing for me. And then the other place where I see it is for this reversal of Commutators, you've got A, B, B, A, so you've got ABBA again, and then I'm not a big fan of ABBA, it's not my style of music, so there's a minus sign in there because it's a negative for me. And so mnemonics, use them everywhere. Wherever I remember them for myself, I'll point them out, and this is a big one, okay? All right, so we've got this. And now what we're going to do is basically just play around with reversing the terms in here, okay? So we could write this not with AB minus BA, but as minus BA plus AB, right? So minus BA plus AB, like so, okay? If we want to do that, we can pull a minus sign out the front. So this would be minus BA minus AB on that side, okay? You can work backwards to convince yourself that's the same as the step above. And then, of course, the thing in the round brackets there is just another commutator, right? So this is just minus B comma A. And so that's how you get this relation that's up here on the slide. AB is minus BA. So if you reverse the two letters in a commutator, you get a minus sign. And when you're handling commutators in quantum mechanics, it's quite common that you end up having to make this transformation to do some of your maths. So it's a very useful one to know how to do. For the rest of this lecture, I actually want to deal with a second commutator, which is kind of a special commutator between x and p of x, because ultimately it's the thing that underpins the one uncertainty relation that you will have seen from first year, which is the Heisenberg uncertainty principle, delta x, delta p of x is greater than or equal to h bar over 2. Okay, I won't get to that form of the uncertainty relation until the end of the week, but here I want to get one of the key commutator relations that we're going to use to get that when we get there, okay? And so it's the commutator between x and p, and I want this for two reasons. One, I want it as a result for later in the week. The other is that I want to give, I always like giving this one because it gives you a bit of insight for a special technique for handling differential operators in quantum mechanics, okay? So what we're going to do here is deal with x and p of x. I'm going to be a little bit sloppy here and just call it p because we're not dealing with momentum in any other direction in this problem for the moment. And what I'm going to do to deal with this commutator is I'm going to let it operate on a function. And I'll explain why we're going to let this operate on a function in a minute. Just so that we don't get misconstrued in here, I'm not actually going to use the wave function psi because I don't want to apply this to anything like psi in particular. All I want to do is have a function as a placeholder. So our function f of x really just has the same properties that a wave function would have, but it's just some generic function. I don't even care what it is at the moment, okay? So if we go in here and expand out our commutator, what we would get is xp minus px. I'll put round brackets on it for the moment. F of x, okay? I'm going to reserve my square brackets for the special meaning of having commutators for this lecture and going forwards. What we would now do is we can multiply that out to the function on two sides. So we can write this as xp f of x minus px f of x. Function is not an operator, so this is perfectly okay. I just can't go reversing the order of my operators. Now what I would do in here is actually write what the operators are in their form. And so you remember from the last lecture, our operator, and so let me just be really specific in here and put hats on so we know what's operators and what's not operators, okay? And these two are operators as well. Okay, so our operator x, as we saw from the last lecture, just gives us a variable x. So this would be x here, and I'll put a dot because I want it to be clear that it's times. And then our operator for momentum was minus I h bar d on dx. And because I'm dealing just with my direction x here, this could be a d rather than a del, right? You don't necessarily need this to be a partial differential equation to be pedantically correct in this particular case. But I often tend to use the partial just to save myself trouble if I end up adding an extra direction to the problem. F of x, and then we've got a minus in here. Now what we have to do is do the second set of operators here. So this would now be minus I h bar d on dx. And then the next one over will be the x, because our x operator will give us an x, and then we'll have an f of x in here. Okay? All right. So I'm just going to move a little bit over to the left here because I need to have a little bit of room to clean this up. What we can do to write this is the first term here, the minus sign can come to the front, the I can come to the front, the H bar can come to the front because they're all numbers, right? So this is minus I H bar. Our x and our d on dx, we can't reverse because they're operators, right? So this will now be x d on dx of f of x, like so, okay? And then cleaning up the right-hand side, the minus and the minus gives me a plus. My IH bar are already at the front, so I've got IH bar. And now my d on dx will operate on the product of x and f of x. So the correct way to write this would be d on dx of x f of x, like so, okay? Now when I work through, and now what I'm going to do is work through and do the derivative. So this would be minus I h bar x df on dx plus I h bar. And of course, now I'm taking the derivative of a product, right? And you know when you take the derivative of the product, if you've got derivative of AB, it will be derivative of A times B plus the A times the derivative of B, right? D on dx of AB is equal to A dash B plus B dash, AB dash, right? So what we're going to have here is dx on dx times f of x plus IH bar x df on dx, okay? Now you're probably seeing why I brought this f of x in. The f of x is in there because now that I've got a differential operator, I have to have the differential operator operate on something. And so really what I've done is just given it something to operate on for the moment. And that's okay as long as I take it back out at the end, all right? What you'll notice is that this first term here and this third term here are the same, so except for the sign. So they're going to cancel each other out, right? This is minus IH bar x df of dx, and this is plus IH bar x of df of dx, and that cancels out. What I'm left with is just IH bar dx on dx of f of x. And of course, dx on dx is just 1, right? Either we're taking the derivative of x, which is a constant, or dx on dx as a fraction is just 1. So this thing is really just I h bar f of x. Now what I can do is think back. At the start, I basically just put this f of x on the right, and here I've ended up with an f of x on the right, and what I can do is just remove it from the two sides. So what I've really got here is my commutator x hat p hat is equal to I h bar, okay? And so all I've really done there is just used the function that I've put in there as a placeholder to enable me to work through the derivative and cancel out the two of the three terms that get me to the final answer. This is a really, really, really common approach whenever you've got differential operators or sort of function operating operators in quantum mechanics or any place where you're doing operator mathematics. So keep an eye on this trip. When you don't have differential operators, you can often live without it. If you have differential operators, you're always going to need it. And in quantum mechanics, you're almost always going to have differential operators because you've got momentum. So you always need this trick. Make sure you don't forget this one. And of course, the first relation that we had at the start means that we can automatically write what this would be if we just reverse these two operators, right? So we would know that p comma x would be equal to minus I h bar, okay? I don't have a good mnemonic for remembering which way these two are around. And it's either quick enough that I can do it myself to get them, or usually it's given to you. Like it's one of these things that very commonly either appears on an equation sheet, and if it doesn't appear on an equation sheet, it's because you're going to work it out as part of the exam anyway. But it's one of these things that I kind of knew how to do very quickly, so that if ever I had to do it, I could get it. Okay. So that's pretty much where we're going to finish today. A short lecture compared to the last one, hopefully just to make up a little bit of time. We now have commutators, the idea that commutators are connected to the ability to observe more than one observable simultaneously. And particularly, we now have a form for a commutator connected to the measurements of x and p. And this is something that we're going to carry into the next two lectures so that we can get ourselves to the Heisenberg uncertainty principle. I'll see you then.